So let me just remind you what we were talking about at the end yesterday. So an important physical insight from this argument of Dyson, that one possible reason for the divergence, the generic factorial divergence of perturbation theory, can be associated with the idea that at some phase of a coupling or parameter, the theory may be unstable. So in the physical phase where E squared is positive, it's not unstable, but the mere fact that it could be unstable at another phase is enough to tell you, possibly, that the theory must be divergent, the perturbative expansion. So I illustrated that with some quantum mechanics examples. This idea here that this system's clearly stable, but if you flip the sign of lambda, it becomes unstable. And perturbation theory doesn't really know the difference order by order between lambda positive or negative. Let me give you now a field theory version of this argument. These are quantum mechanics examples. This is a very old piece of work by Heisenberg and his student Euler, the mid-1930s. In modern language, they computed the one-loop effective action in QED, and they computed it exactly in closed form for a background field that was constant field strength. But diagrammatically, this is what they calculated, all orders of this. So it's only one loop in fermion loop, but any number of external lines, and each external line has a power of E, and by Fourier's theorem, there are even numbers of external lines, so it gives you a series in E squared. And this is actually the very first example of effective field theory, where you have QED, the mass of the electrons and positrons sets a scale. If you integrate out those fermions, you're left with a nonlinear Lagrangian, which describes the remaining low energy degrees of freedom, the photons, once you've integrated out the fermions. Okay, and here's the Maxwell Lagrangian. Here's the first order term, first quantum term proportional to alpha, and you see it's quartic in the electric and magnetic fields. Okay, and this encodes the nonlinear properties of the QED vacuum. So just to show you that you don't have to be able to read this, but just see that this paper of Euler and Heisenberg, they actually didn't compute this series. They computed the full closed form non-perturbative result when the background field was constant. So this integral here is in fact exactly a Burrell integral of the form that I've been describing. And so this complicated looking weird function is actually the Burrell transform of this series. It's quite impressive because in fact this is a double sum because there are two parameters now. It's not just the electric field, there's an electric and a magnetic component. Or if you like, you can expand it in terms of the two Lorentz invariant combinations of electric and magnetic fields. But either way you look at it, it's a double sum. Okay? So you can also do Borel summation with double divergent series. So let me just show you how this goes, and I think this is a very, very useful exercise. This is the simplest example in quantum field theory where you deal with these Borel summations of asymptotic series. So let's specialize to the case where there's just a magnetic field, not an electric field. And then this weird-looking stuff here reduces to something a little bit more manageable, and it should remind you of that example we did in the first lecture of the digamma function. Now, if you expand this and then do the integral term by term, you regenerate this series in powers now of b squared. Okay, and it's b squared because of Fourier's theorem. And the coefficients are these Bernoulli numbers, and Bernoulli numbers grow factorially fast. They grow like 2n factorial, and they also alternate in sign. So you see we're exactly in the situation that we were discussing before. And in fact, the Bernoulli numbers, B2n is minus 2, minus 1 to the n, 2n factorial, I think 2 pi to the 2n. And then there's a zeta function, a Riemann zeta function, which is a sum over integers k to the 2n. So if I insert this expression for these Bernoulli coefficients into here, we see that we can write the coefficients of this expansion as a sum over k coming from here. And this is going to become an instanton sum in a second. And combining the 2n plus 4 factorial and canceling these guys, we're left with gamma of 2n plus 2. And there's a 2 pi to the 2n, so that's part of that beta parameter that I was talking about. And at each order in this k-sum, there's also a k to the 2n. Actually, k to the 2n plus 4. Okay, so these coefficients, if you look at them, for each value of k, they're exactly of the form we were talking about before. There's gamma something n plus something, and it's multiplied by something to the power 2n. Okay? So an exercise for you is to just take that expression that we had before. Now we see that our gamma parameter is 2, our delta parameter is 2, the beta parameter is 1 over k pi. And so for each k, you can just implement that Burrell representation, and then sum over k. And there's this nice identity, summing over k, reproducing this Koth factor. Okay? So what it means is, even though what Heisenberg did originally was just calculate directly this integral, if you were presented with this series representation, the weak field expansion of that, you could reproduce this by these steps of Borel summation. Okay? So I urge you to do this as an exercise. All you need to know is this expression here for the Bernoulli numbers. But there's some very interesting physics going on here, because let's look at this expression. It's proportional to b squared, and the rest is dimensionless stuff. But if you look at this term here, this term scales like 1 over s squared, so when I scale out b, that term is actually independent of b. Okay, so that's the zero field subtraction. The raw calculation is infinite. You subtract the zero field term, which is infinite. And there's a further subtraction. And if you look at this subtraction, it's ds over s, so it's log divergent. So it's b squared log b. And so what's very interesting about this is that from the perturbative weak field expansion, you can regain the strong field limit of b squared log b, which is just charge renormalization. Okay? So from this perturbative series, at any given order, charge renormalization doesn't appear at all. But once you Burrell sum it, you see the logarithmic divergence, and you can interpret that in terms of charge renormalization, which is exactly what Heisenberg did. Okay, so the coefficient at strong field of the b squared log b term is actually the first beta function coefficient. Okay? But this shows that you can gain that from a weak field expansion. Okay, so in this case, you can go all the way from weak field to strong field. Another interesting thing about this is you could have repeated this calculation now not for a magnetic field, but for an electric field. So for a magnetic field going to an electric field, you replace b squared by minus e squared, because e squared minus b squared is the Lorentz invariant quantity. So instead of this being powers of b squared here, it's powers of minus e squared. So now this is not an alternating sum. And if you follow through the argument, you'll end up with a cotangent, not a hyperbolic cotangent. And that now has poles on the integration contour. And if we follow our logic, those produce imaginary parts, which are exponentially small. And physically, this is just pair production. So you produce imaginary parts to this effective action, and they give you the probability of pair production from vacuum due to an electric field background. So the QED vacuum is unstable to applying an electric field, but not to applying a magnetic field. And this is the quantum field theory analog of the difference between the Zeeman effect and the Stark effect. If you apply a magnetic field, you just shift the energy levels in an atom. But if you apply an electric field, you shift the energy levels in the atom, but you can also ionize. So there'll be imaginary contribution to the energy. So this is the relativistic quantum field theory analog of that. And this is known as the Schwinger effect, even though it was discovered by Heisenberg long before. that applying an electric field to the QED vacuum can produce electron-positron pairs from vacuum. Okay? So there's a lot of interesting physics in this mathematically very straightforward calculation, which just requires to know the spectrum of the Dirac equation in a constant electromagnetic field, which is very simple. Okay, so that's one of the exercises. There's an analogous thing for de Sitter space and anti-de Sitter space, but I don't have time to talk about that now. I'm happy to talk about it privately if you want. So let's go back and just recap, because there's an extra level to the story. So far, here's a list of these quantum mechanical problems and analogous quantum field theory problems where perturbation theory is always divergent, and the distinction between alternating and non-alternating was related to whether it was stable or unstable. So that all makes sense, except for these bottom two cases. These bottom two cases are perfectly stable. Right? There's nothing unstable about a periodic potential. There's nothing unstable about this double well. These look like this, like this. Perfectly stable systems. There shouldn't be any imaginary part to the energy. And yet they're behaving in perturbation theory like the unstable systems. Okay? So we have to understand this. So if you've learned anything about instantons or non-perturbative physics, the first examples that are ever given in any review or book are to study exactly these two quantum mechanical potentials, because they have non-perturbative splitting of energy levels due to tunneling. Okay? So I think hopefully everybody is familiar with this sort of argument, at least at the level of Lambda-Lifshitz or something like that. So these degenerate vacui lead to level splitting, either into a band if there are an infinite number of wells, or into two levels if it's a double well. And this is a genuine one-instanton effect from tunneling between neighboring classical minima. And it leads to a splitting that's of the order of exponentially small, with a coefficient which is the instanton action from tunneling from one well to another, divided by the coupling, okay? And with some prefactor. Okay, but the story is a lot more interesting than this. Imagine you tried to do perturbation theory around one of these wells, okay? You discover that, first of all, it's factorially divergent, as you would expect. Goes like n factorial. And the coefficient, this beta parameter, is not s, it's 2s. Okay, so that's a calculation you can do very easily. And that tells you immediately that, remember, by our translation from perturbation theory to non-perturbative contributions, that the exponential corresponding to this type of physics has a 2 there. Okay, it's 2s. And the fact that it's non-alternating in sign tells you that the Burrell summation of this type of series will produce something that's pure imaginary. Okay, so there are two problems here. One is that it's pure imaginary. Second is that even the sign is ambiguous. And so this needs to be understood. And these are stable systems. There should not be any imaginary part, unlike the decaying systems that I mentioned before, where the imaginary part has a genuine physical meaning, and decay allows you to fix the sign. Okay? So there's a very beautiful insight due to several groups around 1980 or thereabouts, primarily by Bogomolny and his collaborators and Zingerstein and his collaborators. And the idea is very beautiful. So we've seen that there's a problem with perturbation theory once we go from the one instanton level to the two instanton level. Something weird. Well, they said, okay, let's look at the instanton gas picture. So this is this idea that you can view this dilute gas of instantons, and at leading order they exponentiate, and that's the explanation of this one instanton effect, that the splitting is e to the minus s over g squared. Okay, so that's, I think, familiar to everybody from these standard quantum mechanical arguments. But now when you go to the two instanton level, you're pretending you have an instanton gas that's dilute of both instantons and anti-instantons. At one instanton level, it doesn't really matter. They're independent of one another. But at two instanton level, they can interact. And instantons repel instantons, and anti-instantons repel anti-instantons, so it makes sense to talk about a dilute gas. But instantons and anti-instantons are trapped. So the whole picture of a dilute instanton gas simply breaks down already at the 2 instanton level. And so you need some way to control this instability. And one way to do it is to analytically continue in G squared. Take it off the real axis, you get a controllable calculation, and then you can rotate back again. And that was the idea of these groups. And in doing so, they found something really remarkable. Just by direct calculation, they found that when you did this, made it well defined by analytically continuing off the positive real axis for the coupling, and then going back again. There were 2 ways to do that. You could either go like this and back or like this and back. And either way you did it, you recovered in the limit going back again an imaginary exponentially small piece, which had exactly the same form as the imaginary exponentially small piece coming from perturbation theory. Okay, so imagine you're analyzing this system 2 different ways. One is just perturbation theory, and you get something that doesn't make sense. And then you analyze the same system at the 2 instanton level using an instanton gas picture, and you discover this, because of this instability, you also get something that shouldn't be there and doesn't make sense. And then you notice that they're exactly the same. Okay? So this is the first observation of resurgence working in one of these quantum mechanical systems, that if you view the expression for the energy not just as a perturbative expression, and not just as an instanton gas expression, but as a combined expression, a trans series, which involves the perturbative expressions as well as the instanton gas summations, then in that combined object, these things can cancel. Okay? So that's the idea. Very, very beautiful insight. So back to pictures, here's the cartoon version of the trans series that shows up in this type of calculation. There's a sum, there's a perturbative sum, there's a sum over instantons, and there's a sum over the interactions between instantons and anti-instantons, which unfortunately I don't have time to show you, but lead to logarithmic contributions from the interaction. And that explains why this sum was cut off. The sum only starts when k equals 2, because you need at least 2 instantons to have interactions between instantons and anti-instantons. Okay? And so by combining these, the sum in the perturbative direction and the non-perturbative direction also in this quasi-zero mode direction, you get a combined object which in principle should be well defined on its own. Whereas if you just look in this direction, you might see some ambiguity. And if you just look in this direction, you might see some ambiguity. And the idea is that the combined object is completely well defined for any analytic continuation of the coupling. Okay? So that's the idea. Let me show you how it works in practice in this problem. So let's look just in the perturbative direction. So I'm going to fix k equals 0 and therefore also q equals 0. So I have a series and it diverges like this. And there's some overall coefficient, some 1 over pi or something like that. Okay? And so that's a problem because that produces something like this, which shouldn't be there because I'm calculating a real energy. So now, the fact that it's going like 2s here tells me I should look in the 2 instanton sector where k equals 2. And you notice that the coefficient of the 0th order in perturbation theory, but k equals 2, so the 2 instanton sector, and 1 power of logarithm, this minus 1 is actually e to the plus or minus I pi. So that produces actually a plus or minus I pi. And the coefficient, this coefficient here, turns out to be exactly the same number as you got from the leading contribution of the large order growth of perturbation theory. So that didn't have to happen. These were 2 independent calculations, okay, which tells you that there's a cancellation between this would-be contribution from Burrell summation and the instability coming in the 2 instanton sector, no perturbation theory at all. Okay? Okay. Let's go one step further. Let's now look at the 1 instanton sector. Remember I said that this splitting was e to the minus s over g squared. So that's a real quantity, and it's genuine physics. There really is splitting of these levels. But it's not just that. That thing is itself multiplied by a series. So the one instanton contribution, the one we learn in our textbooks, is this. But of course, it's multiplied by a fluctuation series as well. And that series is also divergent. And interestingly, its coefficients grow like this, but with a log behavior. So there's a slightly faster growth. And that it's a simple calculation to generate these coefficients. And there are two coefficients here. There's a coefficient of the log term, and there's a coefficient of the term without the log. So again, that's a purely perturbative calculation around the one instanton configuration. If you process this through the Burrell machinery, this corresponds to an exponentially small piece that has 3 s over g squared. It's 3 because it already had 1 here. And because it's 2s to the n here, you get another factor of e to the minus 2s over g squared. So it's this. And this log n becomes a log 1 over g squared, and these two numbers end up over here. Okay? So this thing also shouldn't be there because it has an I. And it's even smaller. It's e to the minus 3s over g squared. So if what I'm telling you is correct, this should be cancelled by something in the 3 instanton sector, where you can have an interaction between an instanton and an anti-instanton, and vice versa. Okay? So we can now go look at k equals 3. And k equals 3 has this factor. And now k equals 3, so q can be 0, 1, or 2. So there are 3 terms here. There's a term without a log, there's a term with 1 log, and there's a term with a log squared. And these logs have this e to the I pi factor here. So each of those logs produces an I pi. So one of them is just going to be a constant with I pi. But here there'll be a cross term, which is I pi times a log. Okay? And the statement is these numbers here in the 3 instanton sector are exactly the same as those numbers there. Okay? So the imaginary parts coming from the Borel summation of the fluctuations around the one instanton are cancelled by something higher up, which are the low-order terms in the fluctuations around the 3 instanton sector. Okay, so as a physicist proof, we've done 2 examples, so it obviously continues forever. This is the idea of resurgence is that this should continue at each order so that the full trend series, including all of the logs, all of the exponentials, and all of the perturbative series, should be completely well-defined, none of these ambiguities, completely real. You only see these ambiguities if you choose to restrict yourself to look at one of the directions, the perturbative direction or the non-perturbative direction. Okay, so you're picking out only a piece of the puzzle, and the combined object is completely well-defined. So that's the idea in the simplest example in physics of this concept I was trying to explain at the beginning, that just an asymptotic series is not well-defined on analytic continuation. Here we see that the summation of this produces an imaginary part that is unphysical, but the full trend series that combines all of these terms is itself real and well-defined. Okay? So that's the basic idea. What I'll show you hopefully later in this lecture is we really understand now that these things happen to all orders in a certain class of quantum mechanical problems, including these. Okay? All right, any questions about that? Unfortunately, this type of argument doesn't generalize very nicely to that Euler-Heisenberg example, because in that case, they're just exponentials. There are no fluctuations around them. Okay, so.
Irrespective of this physics, nice argument. I understand that from your first lecture that there was intrinsic mathematical explanation of that transit from Q being bound by a closure of some operation.
Yeah.
And if you go beyond that, the bound.
What do you mean beyond the bound?
I mean, Q being larger than K, then something bad happens from mathematics perspective as well.
No, all I mean by this is that when you do this calculation in these sorts of problems, the number of logarithms that show up are restricted by the corresponding instanton number.
Yeah, sure.
But that doesn't have to happen. That's a feature of this type of problem.
Yeah. I'm just asking whether there's something intrinsically bad if you try to generalize this defense theory by allowing higher powers of law or something.
No, and in fact, you know examples from field theory. When you try to resum certain classes of diagrams, you generate logs of logs of logs of logs, powers of logs, and there the number of powers can continue forever. Okay? But if you restrict yourself to a given order, you can generate some I pi's at that order, which are not yet cancelled. Right? They may only be completely consistent with unitarity when you resum everything. Okay?
I have a question. So can you do the same thing for the quantum field theory? That there are certain kind of quantum field theories like...
I'm going to show you an example in a second. So, not to this extent, but the leading order cancellation can be shown in certain cases. So this is actually... What I just showed you is this sort of generic structure of resurgence relating large order behavior in one direction with low orders in other directions. Turns out that it's actually much, much deeper than this in these quantum mechanical examples. This goes back to some amazing work by Alvarez and his student, which we rediscovered and extended to some other models, and now we have a very complete understanding of under what circumstances this happens and why it happens. So I want to show you this picture and really talk about this picture to get started. So we want to restrict now to this periodic potential case. You may laugh that I'm just talking about quantum mechanics, but wait a second. So here's a quantum mechanics problem, one-dimensional. I'm writing the energy as U for a reason that will become obvious in a couple of slides. And here's the spectrum as a function of h bar, and here's the spectrum. So what does this picture mean? There's a lot of information here, so I want to go through slowly. And if anything's not clear, please ask. So this is a potential that ranges from -1 to 1. So these dashed lines here are the top and bottom of the potential. Okay? Now you know, for a periodic potential, that inside the wells, below the top of the potential, there are bands, right, in the spectrum. And you know that deep down in the bands, deep down in the wells, the bands are very narrow. In fact, they're exponentially narrow, right? So that's what's being shown here. Small values of h bar effectively means you're looking at energies well below the scale of the top of the potential, namely 1. And so here you see these are effectively just straight lines that are n plus a half, where n is an integer, times h bar. Right? So near the bottom of these wells, these are basically harmonic oscillators. So there's, right? So the energies of those levels are just n plus a half times h bar. Omega is 1 here. Okay, so these are just straight lines with those slopes. Okay, but they're not lines. They're split into bands, and the bands are exponentially small when h bar is small. As h bar increases, the bands broaden. So what you're doing here is you're either doing one of two things. You can think of it as you're lowering the height of the barrier, or you're just looking at energies closer to the top of the barrier. Right? It's the same thing. So you see as you increase h bar, each band broadens. Okay? And so this one instanton formula for the width of the band, just e to the minus s over h bar, works very, very well when h bar is small. But as h bar gets bigger and you approach the top of the barrier, it's clearly breaking down. Okay? I'll say a lot more about that in a second. Now let's look at the picture from up here. Imagine you're at an energy way above the barrier, way above the top of the potential. Now, it's essentially a free problem, because the potential is very small, but it's periodic. Right? It's still periodic. So effectively, you have a continuous spectrum, but because it's periodic, there's a trace of the periodicity that tells you that there are gaps at energies that go like n squared, because it's periodic. Okay? So this is just elementary kindergarten solid-state physics, that there are gaps high up in the spectrum that scale like n squared, whereas low down the spectrum, you have bands whose perturbative energy scales like n. Okay? And you'll also notice that high up in the spectrum, or at larger and larger h bar, these gaps are very narrow. Okay? And you might say, well, they're probably exponentially narrow. Not quite. We'll get to that. Now let's look near the top of the barrier. So right at the top of the potential. If we approach that from this side, from below, the one instanton approximation breaks down, and by the time you get to near the top of the potential, in order to describe properly the width of this band, you need to be able to resum all orders of the instanton approximation. Okay? Coming from here, the gaps become broader, and whatever your approximation was for the width of those gaps needs to also be done to all orders in order to get a good approximation near the top of the barrier. Okay? Okay? And if you look now a little bit more closely, let me guide you. Let's look at this point at the top of the barrier. At this point, this gap is equal to this band in width. It's maybe a little hard to see, but this width here is equal to this width here. This width here is equal to this width here. Okay? Hopefully you can sort of see that. So this is a genuine example of a phase transition. And it's even more than that. When you solve this problem here, how do you do it? You do it using the tight binding approximation, which means you assume that you have independent atoms, and the energy levels of the independent atoms are broadened by tunneling effects, right? But the degrees of freedom you use to describe this problem are localized states in separated atoms. Okay? Up here, you use a completely different set of degrees of freedom. You use plane wave states. Okay? And the gaps are due to this twofold degeneracy at these periodic eigenvalues. Okay? Because you can go this way or that way. Twofold degeneracy, it's just the splitting from that. Okay? So in fact, as you go from here to here, you're using these independent atomic orbitals. You need more and more tunneling effects as you approach the top of the barrier. And somehow that atomic orbital description changes into a completely different description in terms of plane waves. Okay? And likewise, if you come from this direction, you start off describing the problem with plane waves, you approach this phase transition, and somehow your plane waves have to turn into atomic orbitals. Okay? So this is a dream of what we would love to be able to do in QCD. Transition from quark and gluon degrees of freedom to hadronic degrees of freedom. Okay? It's nowhere near as complicated as QCD, but this is the type of thing I want to describe. Okay, so this is also a beautiful example of the large N limit, and that's what I want to talk about for the rest of the time, because often in the old days when people were first studying these sort of non-perturbative effects in quantum mechanical systems, they often concentrated just on the ground state energy, for example. A natural thing to do. It's where the splittings are exponentially smallest. But that would just consider the energy to be, well, I guess I should use U to be consistent. But in fact, we should think of the energy not just as a function of h bar, but as a function of a level number, a number that labels the band or the gap. Okay? And we'll see that just doing that step leads to a huge amount of new insight in physics. And I claim that it's an extremely close analog to the large N limit in matrix models and gauge theories. For example, you can define a 't Hooft coupling, which is roughly h bar n. You can now take n to be large. You can take h bar to be small. And what this parameter does is it basically scans through this spectrum. So think about that for a second. If lambda is small, it means you're talking about a level where n is small compared to this 1 over h bar. Okay? Which means you're talking about something down here. Whereas in this limit, if lambda is large, you're talking about a level that's above the barrier, where n is now higher than fitting n levels into a well that's 1 over h bar deep. Okay? Is that clear? Okay. So this is almost what we want, because we want to now be able to study what happens to a trans series as the coupling runs. Okay? It's one thing to talk about how a series behaves when you have a weak coupling that's fixed. But of course, in field theory, we want to be able to study what happens for an expansion in terms of a coupling, but the coupling can run with some scale. Now here, the remarkable thing is we're talking about a quantum mechanics problem, so nothing's running. The coupling is what it is. But by viewing it in this way, we can actually mimic, to some degree, the running of a coupling. And we'll see that that also works in matrix models tomorrow. Okay, so there's a huge amount of information in this weird-looking picture about transforming non-perturbative physics into perturbative physics and back again, but moreover, perturbative physics changing its character. So for example, we all know that these things, these widths here are given by instantons from tunneling from here to here. Can anybody tell me how to calculate non-perturbatively those gaps? So what is an instanton? It's a tunneling solution from somewhere here to here, okay? Tunneling through the barrier between two turning points. So imagine you have some energy like this, tunneling from here to here. Now, if the energy is way up here, it looks like there are no turning points, right? But of course, there are turning points, but they're in the complex plane. Okay? So you can calculate the solution to the classical equations of motion in the complex plane. You can find a complex instanton that tunnels between the two complex turning points corresponding to that energy. You can evaluate the action on that solution as a function of energy. The exponential of that guy gives you this gap width. Okay? I'll show more details later. So what this means is, this is really an example of this so-called Stokes phenomenon, that as we cross here, we're clearly crossing from one physical regime to another. We're changing degrees of freedom as we cross from this regime to another. And the dominant saddles that are governing this width of bands or gaps is changing from real instantons to complex instantons. Okay? So this innocent-looking problem has a huge amount of physics in it. So the amazing thing is, here I'm writing an expression for the energy. The plus minus refers to the top and bottom of a given band. I'm writing the expression for the bands. There's an analogous expression for the gaps. Let's not worry about that. So there's the perturbative calculation, which is for a given n. So for a given level in this harmonic well, you just do perturbation theory in h bar. Okay? And you'll get an expansion in h bar. The coefficients will depend on n, clearly. They're in fact polynomials in n. But there are corrections. There's the splitting, and the one instanton is an exponential. There's some prefactor stuff depending on n and h bar. And it's multiplied by a series. Okay? And what I told you before was that there was a relation between the large order growth of these coefficients here and the 2 instanton sector. Okay? The amazing thing is I can express this fluctuation expansion completely in terms of this. So here's the form of the expression. It looks a little bit scary, but let's decode it a little bit. The fluctuations around the 1 instanton sector is itself a divergent series. So the claim is I can express that divergent series in closed form in terms of this divergent series to all orders. And here's the expression. It involves a density of states factor. That makes sense because you've got tunneling. So there's a probability of tunneling, but there's a density of states factor. So that makes perfect sense. We will understand where this comes from, and these are just some subtractions that could be included as prefactors, convention. The important thing to note is what enters is the derivative of the perturbative energy with respect to the level number. Now, you might think that's not very well defined, but the coefficients are just polynomials in n, so that's perfectly okay. And there's an analogous expression for bands and gaps. So this is for bands. There's an analogous expression for the gaps in terms of complex instantons.
So applies also in the
Everywhere.
everywhere. How do you see that the gaps between the bands is
Okay, then you have to know what these expressions, how they behave. Okay, so this is quite remarkable. Think of it in terms of this picture of resurgence that I keep drawing. That you've got some certain saddles. The leading one would be, say, the perturbative saddle. And so this, this here is the fluctuation around the perturbative saddle. Okay? Now this expression says that the next saddle with the smallest action is the 1 instanton saddle. And this formula says that the fluctuations around that saddle are completely expressed in closed form in terms of the fluctuations around that other saddle. Okay? So I said before that there was some relation between them. Well, this is the relation in this case. So it's better than that because there's no room on the page, but these dot, dot, dots, which are the higher order non-perturbative contributions, I can also write an expression for those fluctuations also in terms of this, closed form. Okay? So what this means is, this is really an example. This is the first really non-trivial example where you see that to all orders, it's really true that the fluctuations around all the saddles, and now remember there's an infinite number of saddles because I can have any number of instantons, are expressed in terms of the fluctuations around one of the saddles. Let's call it the vacuum saddle. Okay? And it's not just one of these large order, low order relations. It's just an expression. Okay? So hopefully later today I'll run through why this is true. But this, I just want to emphasize that this is really quite remarkable.
Why do you have 2 different lines here?
Sorry, where are you? 2 different lines. What do you mean 2 different lines? Oh, top and bottom of the band. I didn't have room to put cos theta.
I also have a question in that expression. So,
Yeah.
is there any physical meaning of this h bar and the h bar square because it's very similar to
Where?
the
Here?
yes, yeah. So in the previous one, this gives some log term and this.
A little bit because they yes, that's a good point.
Previously, it's related to the
Yeah.
normal.
So in
renormalization.
fact, what you'll see in a second is that it's a renormalization phenomenon. So, yeah, good point. Thank you. Okay, so this picture could extend forever with an infinite number of cells, and it seems to really be working. And in the interest of honesty, I have to confess here that in studying this problem, I actually set out to show that this couldn't possibly be true in a complicated example like this. Turns out, in some sense, it really is true. Now, this is quantum mechanics, but it's actually secretly a field theory, because there's an exact mapping between this spectral problem and a certain supersymmetric quantum field theory, low energy effective action. So the Matthew equation, this periodic potential, is exactly one-to-one mapping to the low energy effective action of this supersymmetric gauge theory. And the mapping goes as follows. There's a moduli parameter in this SU2 theory. There are three different interesting regions, the electric, magnetic, and ionic. There's a scalar VEV, a dual scalar, and there's a superpotential. Okay? Well, if I take this problem here, which I was just studying, I can basically get rid of lambda write it in terms of h bar, and I define A to be the action, roughly speaking, up to a factor of 2, n times h bar. This would be the classical action. Then this perturbative, non-perturbative relation on the previous slide is completely equivalent to the quantum Mattoni relation in that supersymmetric field theory. Just one-to-one translation. If you generalize to the n equals 2 star theory, it's just a different quantum mechanics problem where I replace the cosine potential by an elliptic function, and that's called the Lame equation. Again, a one-to-one mapping between the two. So this is one way to look at something that Shota will talk about tomorrow, the so-called ODE integral model relationship, that you can reformulate the spectral problems of certain ordinary differential equations, I call them Schrödinger quantum mechanics problems. These have certain monodromies. You can re-express those monodromic conditions that give you the spectrum as Yang-Baxter equations. Okay? And so this is one particularly explicit example, two particularly explicit examples, and if I include the double well, that's three, there are more, of a weird relation between something that looks like just simple quantum mechanics and something that is secretly some much more interesting system. And I'm going to actually use that analogy later to be able to give you a proof of this quantum mechanics result. So just to make it really concrete, this U was the moduli parameter. As we discussed, it was completely clear that there were three different physical sectors in this problem, where U is close to -1, where U is close to 1, and where U is close to infinity. And they map directly to the electric sector, magnetic sector, and ionic sector. And it's not just an analogy, it's an absolutely quantitative map between them. And I can tune between these sectors with a 't Hooft coupling, which is essentially n times h bar, or maybe n times h bar over 2, into these regions where lambda is very large, very small, or close to 1. Okay? So your comment about the renormalization is a good one. Okay, so I'll be fleshing this out as we go along. Any questions at this point? I don't expect you to understand this at this point. I'm telling you a strange fact.
Can you take a continuation to cosine hyperbolic
Yes.
rotation?
Yes.
Then some relationship exists between this spectrum.
Yeah. In fact, let me comment on that. Thank you. So the cosine potential is periodic, right? The elliptic version of the cosine potential is also periodic, but it's actually doubly periodic. It's periodic in the complex plane. It's periodic along the real axis, and it's periodic in the imaginary direction also. Okay? So if you want to go from cosine to hyperbolic cosine, you can take the real period to infinity and just be left with the imaginary period. But this is a very interesting example, which we studied because of the following. Remember, I told you that the large order growth of the perturbative coefficients should be determined by twice the instanton action, right? That should go like n factorial with twice the instanton action to the power n. So that works beautifully in these cases. But if you do it for this Lame potential, which is perfectly real and periodic on the real axis, it fails. So you can calculate large orders of perturbation theory very easily, and you can calculate the instanton very easily, and you just compare them and it doesn't match. And the answer is that the Lame potential is doubly periodic, so there's also a complex instanton in the game, even though you're doing real physics along the real axis. So if you evaluate the action of that complex instanton and take it into account, now you match the large order growth. So this is an example where another saddle somehow appears. And so this is a case where if you didn't know that and you studied the large order growth, you would discover that there must be some other non-perturbative object somewhere other than the real instanton that you calculated. Okay? So the whole picture seems to fit together quite nicely. But that's one way of tuning from the cosine to the hyperbolic cosine potential. So what about supersymmetry? This is something that is often raised as an objection, because in supersymmetry the ground state energy is 0 to all orders perturbatively, so how on earth can that encode non-perturbative information if all the terms are 0? Well, the answer is it's not just the ground state energy that's important, you also need the density of states. You need the derivative of the energy with respect to the level number. And so it turns out, in cases where there's broken supersymmetry, even though the perturbative energy at the ground state level vanishes to all orders, its derivative with respect to n does not vanish at n equals 0. Okay? So this formula is actually still true. Okay? So you can have the situation where the ground state energy is perturbatively 0 to all orders. Using this expression, you can calculate this dE dN at n equals 0, and this will give you the non-perturbative supersymmetry break. Okay, so you can check this in many different examples. Okay, so that's interesting. Now you can look at an example like the supersymmetric version of the periodic potential, where supersymmetry is actually preserved non-perturbatively. And that turns out to be an interference effect, a cancellation between two different saddles. Okay? So again, this could have been an obvious objection. This couldn't possibly work in supersymmetric theories, but it does. All right, so where am I going? Okay, so let me just fill in a few more details here. So this is what the perturbative series looks like. This is the bottom of the well. This is the harmonic contribution. And then there are contributions in higher orders in h bar multiplied by polynomials, and it's more natural to write it in terms of n plus a half instead of n. But this series is divergent as a series in h bar for any given n. And you also see that this doesn't really make sense anymore if h bar times n is big. Then it's not the right way of writing the expansion. So that would be lambda big. So this is really a small lambda region. Now you can look at large h bar, which is this gap region. And if the US government weren't shut down at the moment, you could look this up online. But if you try to do so, you get a message telling you that you can't look up this formula. But here's the formula for the location of the gaps. And there are poles in all these expressions at integer values of the gap label. And those poles are a signal that this sort of perturbative expression is not actually correct. There's something missing here. And what's missing from this expression is exactly the non-perturbative splitting of the gaps. So you should think of this as the real part of the Burrell summation of this will give you the center of the band, and up to an appropriate n, this will give you the center of the gap, but there are extra non-perturbative effects. And so this is well known in the solid state literature, that the splitting of a band to leading order is given by a density of states factor times the exponential of the, the real instanton. What is less well known, but nevertheless true, is that the splitting of a gap is given by exactly the same expression, but in terms of the complex instanton. Just for this argument I gave you, that the only turning points above the barrier are complex turning points. But these are leading order expressions, and basically what I'm saying is that these things get generalized to all orders. Now, if you do this, this function as a function of energy is different from this function as a function of energy, right? You're integrating between this turning point and this turning point. It's a function of the energy. But if you've got two complex turning points up here, that will give you some other function of the energy, right? So it turns out that when you put this in for the band, you get this familiar exponentially small piece with a prefactor that's powers of h bar. But from the complex instantons, you get an exponential of a logarithm. So in fact, the splitting of these gaps is power-like, not exponential-like. Nevertheless, they really are instantons. Okay? They're complex instantons. And there's an important message here, is that the real instantons generically give exponentially small contributions, and complex instantons generically give powers. And in fact, these series here for the center of a gap are completely convergent for any n. Nevertheless, there's an underlying instanton structure, trans-series structure, but in terms of powers instead of exponentials. So that's quite a relatively recent observation, and nevertheless, all these relations between instanton sectors and perturbative sectors still hold, but you have to somewhat enlarge your viewpoint of what an instanton expansion is. And hold on, one more comment. The transition region, in this case, turns out to be when nh bar is 8 over pi. There's some particular number. That's sort of order 1 in my, yes.
Yeah, naively, it's a naive question, but in the real time,
Can you speak up? I can't hear.
In the real time, real axis, I can see that this is a turning point, but in the complex plane, depending on the angle, you may or have many turning points.
No, turning point is cosine x equals energy, right? So x is just an arc-cos function up to 2 pi I n. So it's very simple. It's not subtle at all. So it'll take you one line to see.
Okay. So there is in the complex plane there is always one turning point.
Between neighboring turning points, just like in this case. Right? There's an infinite number of turning points here, but the instanton is between neighboring turning points. Okay? So there's real physics here. So let me show you. This is bread and butter physics to atomic physicists and laser physicists. Exactly this problem happens when you change from ionization just being tunneling due to a constant electric field, which is a linear potential, to a time-dependent electric field that's monochromatic. So this calculation was done by Keldysh in the early days of lasers. And he noticed that there's a dimensionless parameter, gamma, which is roughly speaking the ratio of the binding energy of the atom to the scale set by the electric field and the frequency. And if you do a WKB analysis, you get an exponential factor times this is some arc sine or something function of gamma. And when gamma is small, that means it's roughly a constant electric field. This G reduces to 1, in which case this is just the standard tunneling picture through a linear potential, which everybody does in their first quantum mechanics class. But in the other limit, where this field is oscillating very fast compared to the scale set by the peak field and the binding energy, this function becomes a logarithm. So this exponential of a logarithm becomes a power. And if you look at this power, you recognize what it is. This is the strength of the field relative to the energy scale of the binding. And this number here is twice the binding energy, so there's a 2 because this is a probability. It's the binding energy divided by h bar omega. So this is telling you that you don't ionize by tunneling, you ionize by going over the barrier. This is multi-photon ionization. The number of photons you need is the number of h bar omegas to make up the binding energy. Okay? So this is an absolutely precise analog to what I just told you before about the periodic potential. It's the same problem. So there's a regime where ionization is non-perturbative and tunneling. There's a regime where it's multiphoton ionization. And the transition between the two is where this 't Hooft parameter is of order 1. Okay? And this is textbook material for strong field laser atomic and molecular physicists. And you see that what's happening here is there's genuine physics that these are real instantons and these are complex instantons. And the complex instantons give you this power-like perturbative behavior, but high-order perturbative behavior. Whereas the real instantons give you these exponentially small things that we're used to describing instantons as. Okay, this can be upgraded to this Schwinger effect that I told you about before. Instead of a constant electric field, you can do it a time-dependent electric field. This was done by Brezin and also independently by Popov. It's exactly the same story. There are complex instantons. Okay. All right. Any questions about that so far? So I've told you some very strange things. But I think if you think about them physically in terms of these ionization pictures and splittings of bands and gaps, you get a little bit more physical intuition for why there are these two different types of instantons and how you can have a transition between dominant or other saddles as you change a parameter in the theory. This isn't the whole story when you come to field theory. So the field theory examples I've showed you are fairly limited. One's a supersymmetric field theory, so it's special. The other one was this background field calculation, which is also special. No running coupling or anything there. Let's now talk about a real problem, like Yang-Mills. So an asymptotically free quantum field theory. Now in quantum mechanics, the basic reason for divergence and perturbation theory is combinatorics. Just that the number of diagrams grows factorially. It's as simple as that. And the factorial of the divergence can be traced to this rapid growth of the number of generic diagrams. The details depend, of course, on the interactions and whatever, but that's the basic reason. When we come to field theory, there's a new source of divergence. So there is still the divergence due to the rapid growth of the number of diagrams. That's still important, and that's related to instantons. But there's a new source which is related to the running of the coupling. And these are called renormalons. And it turns out it's a faster source of divergence. And remember that the rate of divergence, right, the coefficient in the rate of divergence tells me the exponential factor, right? It tells me the exponent in the non-perturbative quantities. So a faster rate of divergence means the thing in the exponent is smaller, so it's a dominant non-perturbative effect. Okay? So in fact, these renormalons lead to a growth in perturbation theory that is n factorial over twice the instanton to the power n, but there's an extra factor which is the leading beta function coefficient to the power n. And that beta function coefficient in a typical theory scales with capital N. Okay? So what that means is the effective coefficient in this exponent is not 2s. The effective coefficient is going to be 2s divided by something, and that something is going to scale like n, so typically bigger than 1. And there are both positive and negative Burrell singularities. And this infrared renormalon puzzle, which you can read about in 't Hooft's Ereche lectures, is that the poles, due to these infrared renormalons, so in asymptotically free theories, there are infrared renormalons which show up on the positive Burrell line, so these are the problematic ones. They don't line up with the instanton-anti-instanton poles. Whereas the Bogomolny-Zinjo-Stan argument was that this non-perturbative stuff lined up with the Burrell singularities coming from the Burrell analysis of perturbation theory. So there was a cancellation. So the argument here is that perturbation theory, these renormalons produce exponentials like this, and they're imaginary because the infrared renormalons have perturbation theory that doesn't alternate in sign, whereas instantons on either R2 or R4, depending which theory you're talking about, produce exponential factors like that. There's a mismatch of beta 0, which means that these can't possibly cancel. So that was the infrared renormalan puzzle. So it turns out there's a very nice solution to this, which is actually where we started studying resurgence in field theory, was that, let's talk about the CPN model in 2D. I realize, unfortunately, I don't have time to define the CPN model. If you're not familiar with it, just think of it as a two-dimensional analog of Yang-Mills. It has instantons, it's asymptotically free, it has all this transmutation of charge, just like in Yang-Mills. And it has this problem that it also has infrared renormalons. But there's a way to control this theory using twisted boundary conditions, which is in very similar spirit to what Sok was talking about yesterday. And then you produce leading non-perturbative objects called neutral bions, and remarkably, their contribution lines up exactly with the renormalan singularities. Not only does the exponential factor match, but also the prefactor. So this, you're asking about an example in quantum field theory. So this is the leading resurgent cancellation, analogous to what Bogomolny and Zingerstand did. We don't yet have any concrete information about the higher order fluctuations in a non-trivial asymptotically free theory like this. So I'm not going to go through all that. Let me point out that this actually raises some serious puzzles for this whole picture of saddle point decompositions of path integrals, because there are other 2D sigma models that also have renormalons. So remember, renormalons are sort of a problem, infrared renormalons are a problem in the perturbative sector. Okay? So there are theories such as the ON model when n is bigger than 3, and the principal Cairo model that have no instantons. And yet, in the perturbative sector, they have this infrared renormalan problem. So it looks like the entire discussion is a dead end, but it so happens that these theories, even though they don't have instantons, they have regular, finite action, quantized action solutions to the second order equations of motion. So remember, the saddle is a solution to the second order classical equations of motion. It just so happens that instantons are solutions to first order equations corresponding to minima of the action. But saddles are solutions to the second order equation. And these things have some very interesting topology, such that they have finite action, quantized action, non-BPS saddles. These were known in the literature for a very long time, but they were somewhat neglected physically because they had unstable modes, because they're not minima, they're saddles. So it turns out that these things play the role of these instanton-antinstanton molecules. The instability of these things produces imaginary contributions, and these things, these uniton-type objects is what they're called, play the role of these neutral bion molecules of instantons and anti-instantons in these cases. This raises an interesting question because Yang-Mills theory also has non-BPS solutions, finite action. These are also not very well known. There's a very, very simple example, which I would like the students to think about, which is consider SU4 Yang-Mills. So you know it has instantons, you know it has anti-instantons, right? Let's take a 4x4 representation. I can put an SU2 instanton here, and I can put an SU2 anti-instanton here, and I can put 0 here. That thing is clearly not an SU4 instanton. It's not an SU4 anti-instanton. It's clearly a solution to the second order equations. It's clearly completely fine. It's not irregular, has quantized action, has 0 topological charge. I can put these instantons wherever I like. So it's a genuine, well-behaved saddle of the SU4 Yang-Mills functional integral. So question, what is its physical significance? Okay?
It is not gas or so it is not anti-instant or instant pair, and it is not.
Well, if you put them far apart, it will look like an instant-on anti-instant-on pair, but I can put them wherever I want. I can put them on top of one another. Okay? I can play with their relative rotation. They are absolutely genuine saddles. So a reasonable question is, what's their meaning in terms of semi-classics? And I don't know the answer. So I hope one of you may be able to find the answer. The technical problem is that the fluctuation problem around this is complicated. The fluctuation problem around instantons is simple, and the fluctuation problem around anti-instantons is simple, but the fluctuations around the non-BPS solution is not very well understood. So that's a, yes? Yes?
I'm a bit confused by the question because the things that actually contribute to this exponential piece is really always instanton and, or I should say topologically trivial saddle configuration. So you didn't quite need topologically non-trivial instanton to begin with.
Right, but this thing is topologically trivial.
Right, and if you
Yep.
have such a thing,
Yep.
of course it's instanton, some variety of that.
Mm-hmm.
Even if you do not have topological instanton, I mean, why are you worried about that at all? As long as you say, as long as you have this saddle configuration, that can play the role of this bion, for
Yeah,
example.
okay,
neutral
okay.
bion.
So maybe I gave the wrong impression. Not worried about their existence, it's just the calculation is much harder with these objects. Let me just put it that way. So these I think are attributable to this physics, but it's just technically much more difficult to study the fluctuations around one of these objects than it is if they're instantons. Or if they're instanton gas widely separated instantons where we can just do the usual thing. Okay? That's what I meant. Okay. How much time do I have? 5 minutes. Okay, then I think, let me just, where am I going? All right, so I think I'll probably stop there. I was hoping to give you a proof of these quantum mechanical relations between perturbative and non-perturbative effects. I think I can do that quickly tomorrow. And then I want to change gears to talk about a matrix model, the Gross-Whidden Whidden unitary matrix model, which has a free energy, which is also a function of n, where n is the size of these unitary matrices, and it has a coupling which plays the role of h bar. And it's almost the identical problem to what I just described for this periodic potential in quantum mechanics. But we can start invoking some results from Painlevé equations and integrability to generate the trend series structure much more efficiently. And we can look at different types of limits. So we can fix n and look at weak coupling. Or we can fix n and look at strong coupling. Or we can fix coupling and look at large n. And we can fix 't Hooft coupling and look at large n. And we're calculating the same quantity. And yet the expansion of the same quantity in these different limits is completely different. Right? So we want to understand in detail what types of structures can appear and how they can change from one thing to another as you change a parameter. Because these are the sorts of questions we need to be able to understand when we come to do something like large N analysis of Yang-Mills or something like that. Okay? So it's a little bit unfortunate that I'm not going to be able to go further than matrix models to quantum field theory. But already at these levels of these quantum mechanical problems, I think they're nice because everyone here can understand it's not very sophisticated mathematics. And yet you learn a lot of intuition about how these phase transitions can happen as different saddles change into other saddles. And hopefully that'll be a guide for applications in more complicated field theories or even string theories. So that's for tomorrow. Thank you.
So nowadays we have lots of interesting results of PMP relations for differential equations. So my question is, do you believe there could be some PMP relations in four difference equations?
Yes, definitely.
Definitely.
Yes.
But because some time ago, with my collaborators, we considered the Hofstadter-Hamiltonian, which is a generalization of Matrices equation, but we failed to find such a PMP relation.
There are some results about that now. So,
Okay, I see. Okay.
Yeah. It's a little more mysterious. So what the question is, I've been talking here about problems where the underlying structure is a differential equation, and we can use standard WKB type techniques. And so there's a WKB formalism at the discrete level, invented long ago. And that can be used to do trans-series for difference equations, not differential equations. And the whole structure is there. And so in this particular Hofstadter model, there are results now for relations between, let's call it these perturbative, non-perturbative relations. They're not understood, I think, at the same level as now we understand these quantum mechanical versions, but there are beautiful calculations that are completely convincing that these relations are there. And I think it's a very interesting question to try to understand it more deeply.
I see. Okay, thank you.
Okay, so I have a question. This is more a question about terminology, and we call instantons because we can view them as point-like objects in time direction.
Okay, yeah, it's bad terminology. Let's just be honest and call them saddles.
Okay, so I was just going to ask why we call renormalons.
I didn't. Tough to.
Okay.
No, it's actually a very interesting question because it's an issue with perturbation theory, right? It's from classes of perturbative diagrams that give you a factorial divergence. So ons is usually restricted to non-perturbative stuff, right? So Tuft had this expectation that there should be some non-perturbative semi-classical interpretation of these singularities in the Burrell plane. It just took a very long time to understand what that is. But don't confuse. So renormalin is really an issue in the perturbative sector.
It's about the one you drew on the board. So what's the meaning of SU2 instanton in SU4?
Or you can embed an SU2 instanton into SU4.
Oh.
Right. This is just a very, very simple example of how you can see a completely well-defined solution in SU4 that's neither an instanton nor an anti-instanton.
Okay, if there is no more question, let's thank the lecturer again. This will be the end of the morning session.